So the big issue with compaction is the idea that you're going to have these very small pores. And so with having the smaller pores as opposed to the larger pores, you're not going to allow water to move into the soil as well. You're not going to allow air to move into the soil as well. And when that happens, then the water and nutrients move very slowly through the profile. And basically, if you're trying to have plants or anything grow in the soil, it's going to be hard for them to grow if they can't get air and they can't get water very easily. Whereas in a well-structured soil, they can get water and air and different amounts of it very easily. So when we're talking about, back up for a second, there we go. When we're talking about plant growth, we really want to talk about the idea of nutrients. So what does the soil actually provide the plants with? So one of the big things to think about that soil provides plants is just physical support. The actual idea that a plant can grow up nice and straight and get towards the sun. Think about trees. Trees really want to get towards the sun and grow tall. The way they can do that is if they have the physical support of the soil. The tree or the plant gets rooted into the soil builds around the roots and holds it in place. The other idea is that the soil provides the plant with water and air, and that becomes crucial to our understanding before, that if half of soil is just space open for water and air, that makes total sense, because that's how it's going to get this system going, where it's going to provide water and air to the plants, and then that way the plants can use the water and air. It also provides essential elements in terms of nutrients. So when we look at this list on the bottom in terms of macronutrients, so big nutrients and micronutrients that the soil provides plants, the biggest and most important one is nitrogen. It's the most important and it's the most abundant. And we talked about that before with the idea of nitrification and denitrification happening in the soil in terms of chemical cycling of the soil. And so the soil provides nitrogen to the plants. And so that's a really important idea, that's what soil is there for, that it's going to be able to give the plants the most important nutrient that it needs. If you go and buy fertilizers, usually most common fertilizers you'll see is like a 10-10-10 or an NPK. And so what that means is nitrogen, phosphorus, and potassium, and it's a combination of those three nutrients that is in the fertilizer, and it's going to help the plant grow. Backing up, there we go. Soil pH is the single most important chemical property of the soil because it affects the chemical, physical, and biological properties of the soil. So knowing the pH of the soil will allow you to determine if the soil is suitable for plant growth and what nutrients will be most limiting. And that's really important because we just saw that list of all those different nutrients. And so if we're really thinking about, well, what nutrients do we need, or how can I make this better? That's where pH comes in, because the other things, when you look at like soil structure, it's going to be kind of obvious, and soil texture, they're going to be a little bit more obvious, right? If my land holds water really well, but the water doesn't drain away, then I know I've got a lot of clay in my soil. If the water comes in, like where I lived in Georgia, if it rains like 6 inches in a day, and then you have water that day, and then the next day all the water's gone, then you're like, oh, I definitely have a lot of sand in the soil because it doesn't hold water at all. Pretty obvious. If you have something like out front of our classroom where you get a lot of traffic, so you can see that soil in those areas have compaction issues. And the way you can tell is you can see that grass is growing in certain parts out front. But then there's parts where it's just bare. And you know that they're getting water. You know that they're getting fertilized. But it's still bare. And that's because of all that compaction causing bad soil structure and not allowing the water and the air to be able to get to the grass to allow it to grow. So that also becomes obvious. But when it's not obvious, that's where testing the soil pH and understanding the kind of the chemical properties of the soil are really going to become important. The other part where it's really important is the idea that pH determines nutrient availability. So if your pH isn't in a certain range, it's going to be very hard. It's going to basically tell you exactly what you need, because certain plants are going to be basic or alkaline. Certain plants or soil are going to be acidic, and you're going to need different nutrients. So what am I talking about? So let's look down here at the bottom right. So you see that neutral area. So water is something that's neutral, and neutral works well for us. So there's basically an acceptable range of soil from 5.5 to 8. But really, if we're really talking about what is the best range, we're talking about 6.5 to 7.5 is where we'd really like to be. So if we want our best pH for soils to grow plants, we want it to be between 6.5 and 7.5. But we're okay between 5.5 and 8. If it's less than 5.5, you have an acidic soil. If it's higher than 8, you have an alkaline or a highly alkaline soil. And we can see that it says if we have an acidic soil, we're going to need to apply lime. And if we have an alkaline soil, we might want to consider some different species. So why does that become important? Well, now when we start to think about it, this is what becomes pretty interesting to me, is that most soils actually are on the acidic side. So we already know that we're not going to line up perfectly. Most soils range somewhere between more like 4 and 7 for the most part. And so when we think about that, we know we're already going to have to help out some of these soils. Now, when we look at this bigger graphic on the top left, you can see things like potatoes, carrots, onions, lettuce, tomato, cabbage. See how all of those fall to the more acidic side? So we already know that we're going to need to do things to our soil in order to help get that pH to that real ideal growth, where we said we really would like plants to be between 6.5 and 7.5. You can see those plants really fall in our range that it's okay, that 5.5 to 8, but really we'd prefer it to be 6.5 to 7.5. And so you can do things like add fertilizer or apply lime or do these different things in order to really get your plants into the right range. So here's just a picture of the United States and the different pHs in the soil. And so the average for North America, including Canada, is about 6.4. So just outside of that real ideal range that we want, but definitely in a range that's ideal for plant growth. And so you can see California with the color that's there. It's right where we want it to be. It's a kind of a golden color, so it's slightly darker, but around 7, which makes sense as to why we can grow so many things in the state of California. But you can see the other places, especially the eastern United States, very much more acidic soils in the eastern United States. So 5 factors that affect soil formation. So when you get to thinking about soil formation, what I really want you to think about is the idea of how did this all start? How did we get soil? So we talked about the idea that the sun starts this whole process. Well, the sun hits the planet, okay? So what was here way, way back when, millions of years ago? There's a big rock, okay? So we get the rock, we've got rock, and we've got water. So we get the sun that heats everything up and gets the weather patterns going. So then now we've got the rock and we've got the water hitting the rock, and now we get weather going because we got heat and water. So now we can get air and have air patterns moving. So we've got air and water. And what basically happens is just over this long amount of time, that rock gets hit by air and water, and the big piece of granite for this area becomes smaller pieces of granite, becomes smaller rocks, and then all the way just eventually keeps weathering and weathering and weathering and weathering all the way till you have that one layer of bedrock, then you have weathered bedrock, and then you have soil where the rocks have just broken down and broken down to where you just have it building up on top of each other, and you just have these smaller and smaller pieces until you have soil formed. So how did that happen, or what are the influences that make that happen? So one of them is the climate. The climate determined the flora and fauna, the rate of development, nutrient leaching, organic matter, the biota. So what plants were there providing nutrients eventually, what how much organic matter was getting into the system. Like, did you have animals there? Were they dying and pooping and having that happen? Because that can affect the rate of soil development. Your topography. So, like here in the Central Valley, you've got lots of water funneling down from the mountain ranges and giving us a lot of groundwater underneath. So having water that's working its way through the soil all the time was able to help us get nice fertile soil here. Whereas the mountain ranges don't have as much fertile soil because all that water was eventually running off into the valley. Your parent material. So for this area, it's a lot of alluvial parent material. So water deposited sediments. The Kern River floodplain is basically all of Bakersfield. At one point in time, the Kern River was big enough that all of Bakersfield was underwater, and it all flowed out towards the Pacific Ocean. And now it's not that way, but it was for so long that a lot of the sediment and a lot of the soil that we got is not just also from the weathering. It's from the weathering of the granite, but then also from the Kern River bringing soil downriver and down into this area and having it kind of settle on top of that weathered granite soil as well. And then the idea of time. I'm talking about thousands and millions of years to make this soil develop. So time is crucial in the idea of soil formation. And all of these factors are linked together. It's not, well, it was like 1 and 3, or it was 2 and 4 and 5, but not 1 and 3. No, it's all 5 of these things linked together that get you soil formation. But the one that you really, really got to think about is time. So only the top few centimeters are productive in the sense of being able to sustain growth. Like I was saying, topsoil, you're talking about like 6 to 8 inches where the roots usually grow. It takes hundreds of years to form 1 inch of soil from parent material. So now with other influences like getting soil from taken down river like we have here, or having animals and other things dying and pooping and doing all these other things that can enrich your soil quicker. It can happen quicker, but just the idea of you just have parent material and we're going to wait and see how that parent material turns into soil, that can take hundreds of years to just get 1 inch. So now the next part of this lecture, we're going to kind of talk about the soil layers. And another word for layers is horizons. So when we talk about a soil profile, we're basically talking about looking at all the different layers within a piece of soil. And so we are going to focus on 5 horizons. We're going to focus on the O layer, the A layer, the B layer, the C layer, and the R layer. So starting from top to bottom, you have your O layer, which O means organic, and that's where you're going to get your humus and your big buildup of organic matter. Soils usually, if they're higher in organic matter, they're darker. So if you have rich topsoil with lots of organic matter, it's going to be dark soil. And if you have soil that doesn't have a lot of organic matter in it, is not very rich in organic matter, it's going to be lighter colored. So in the desert, you actually don't have an O layer, and you see that lighter colored soil because there's not a lot of organic matter. So then it's not surprising to you that a lot of stuff's not growing in the desert because there's not a lot of water, there's not a lot of organic matter, you don't see these dark soils, so you know there's not a lot of good stuff in the soil out there. Underneath the O layer, you have the A layer, and that's going to be our layer of topsoil. Now, people get confused by this all the time. It's called topsoil because it is the top layer of soil when working your way up from the bedrock. But the O layer, that's organic matter. It's mostly that humus that I was talking about. So where it's that partially decaying material, where it's not quite twigs and leaves and animal poop and dead animals. It's not that stuff. But it's also not quite soil yet. It's the stuff that's about to become soil and work its way into the system. So that layer's on top. And then right underneath that is the topsoil. Underneath the topsoil, you have the subsoil. Now, the majority of roots are going to be in the topsoil. They're going to be in that first 6 to 8 inches. And you can still get roots in the subsoil. By the time you get down to the C layer, that's going to be our weathered bedrock or our parent material layer, you're not going to see the plant roots going that deep. So that's actually down there is where we're going to find groundwater. Because if we think about how groundwater would work, the only thing we have below the parent material or the weathered bedrock is bedrock. So we have the big slab of rock. And so because of that, when water trickles down in through the system, it's going to hit the bedrock and start piling up from there. And so in that C layer is where we're going to see a lot of where we would find groundwater. Well, why doesn't it keep going all the way to the top? It does in some places. In some places it doesn't, because you have roots from the plants and other organisms within that soil using the water. So up above in the topsoil, subsoil, and the A layers and B layers, you're not going to see the big reservoir that you would see of groundwater down lower. Also, think about weathered bedrock. So we said bedrock's like one big slab of rock. So weathered bedrock is just big pieces of rock. There's a lot. It's very easy for water to pile up there, and it's very easy for water to just sit there, because remember, above that you have soil, and soil, we said, is half water and half air. So then if it's soil up above there and the bedrock is much more of substantial pieces of rock, it's not going to soak up that water as much and use the water and be trying to transfer it to plants. It's going to just hold it there and let it sit there much longer. So starting from the top, our layers are O, A, B, C, R. Organic matter, topsoil, subsoil, weathered bedrock or parent material, and bedrock. O, A, B, C, R. Organic material, topsoil, subsoil, weathered bedrock or parent material, and then bedrock. So just another way to look at it, the idea that we've got all sorts of things happening right towards the top. We've got that nice surface litter layer, so that's our organic layer. Then you can see the roots in the earthworm, that's going to be our topsoil. Then we're going to have our subsoil, and then eventually we're going to get down to our parent material, and then our bedrock. O, A, B, C, R. So for a typical grassland soil, that's what we're looking at, the O, A, B, C, R kind of setup. You can see in this slide it talks about an E layer. So it says it's used for horizons that have a significant loss of materials through eluviation. So in forested soils, sometimes you can have an E layer in between the A and the B. But for the most part, when we're just talking about a typical grassland soil, this OABCR is going to be our normal idea. So I kind of already went over this, but the idea that the O layer is going to be rich in organic matter, that's where our plant litter is going to be, and in desert soils you're not going to have this O layer. For the topsoil, this is where you're going to see a lot of plant roots, about 6 to 8 inches. If it's got a lot of organic matter, it's going to be a dark colored soil, and the darker the soil, the more organic matter it has in it, and usually has a granular texture. So like I said, if it's a forested soil, in between the A and the B, you'll have this E horizon. And the E horizon, it's going to be lightly colored because basically it's going to have a lot of material leaching out of it. So when we say leaching, that means it's the idea that it's going to, they're going to be, the nutrients are going to be lost out of that layer. So the A layer is full of a lot of nutrients. That's why you get a lot of plant roots in there, because that's where they want to be, because that's where all the nutrients are. But if you have it to where precipitation or irrigation is forcing those nutrients farther down, then you're going to end up with this E layer, where it's going to be this light colored layer, where it's because all the nutrients have leached out and leached down into the next layer. But this is only found in forest soils. So if we say a typical grassland profile, we're talking about OABCR. If we were to say a typical forest profile, we would say OAEBCR. So the subsoil, the B layer, lighter colored because it's got less organic matter in it. Plant roots are usually still present here, and it's usually richer in iron and aluminum compounds, and there's usually more clay to it, which, if you think about it, that also kind of makes sense, because we want our soil to have good structure to it and be able to be solid and whole and be the foundation for everything happening above. So a little more clay to where it's has a little more structure to it, and it's not so much sand and silt and loamy soil that'll kind of move around very easily. Clay is much more structured to where you can make it to form it and make it harder and make it much more of a solid foundation. So our C layer, it's our parent material layer or our weathered bedrock layer. It usually contains pieces of rocks and borders the bedrock. Usually no plant roots are here, and it's usually saturated with groundwater. And then I just threw in here the R layer, which is bedrock, and you can see it on the picture there on the right, which is just the idea that you hit that one layer of rock and there's nothing that penetrates through there. It's just the one layer of rock. And eventually, if you want to learn about what happens under the bedrock and keep going all the way to like the core of the earth, that's where geology class and that sort of thing would be your next step in figuring out more about that. So like I said, in a grassland soil, this is going to be our typical idea, this OABCR. We've got our leaf litter, organic material on top. We have our A horizon, our topsoil, where it's got that darker color because it's got a higher organic matter. We've got our B horizon, which is going to be our subsoil. Eventually we'll get to our C horizon, which is going to be our weathered bedrock or parent material. And then we're going to hit an R horizon, which is just the hard bedrock, which is the rock that everything formed from. So the second part of this class is going to be soil erosion. So I'm going to stop it here and do another recording where we go into soil erosion.